Okay.
Hello, welcome to our presentation.
My name is Abdullah Rabai.
My name is Matthew Benavides.
My name is Romero Panzola.
And I'm William Messick. So our topic today is the DART mission, the first planetary defense test. In other words, Defying Doomsday, NASA's mission to alter our cosmic destiny. So in order to start our discussion about this, we're going to move our focus to asteroids. We can go to the next slide. So asteroids are small rocky objects that orbit the sun. So what makes them special is that they're irregular shape and they're covered in craters, as opposed to something like a dwarf planet, which would be a spherical shape or planet. And they usually range from about 1 meter to 500 kilometers. So they can be pretty small, about the size of a person to size of a city. And additionally, they move extraordinarily quickly. They move 17 to 25 kilometers a second, or 38,000 to 55,000 miles an hour, which is faster than anything man-made. Another thing to note is that asteroids do not have an atmosphere, which is something more that you would see on a planet or a comet. And so we have been able to catalog over 160 large impact craters on Earth. The largest one that we know of is over 300 kilometers wide. And one interesting crater of note is the Chicxulub crater in Mexico. So this is actually the crater that caused the massive extinction of the dinosaurs. And when this made impact with the Earth, it gave off over 1.5 times 10 to the 24 joules of energy, which in other words is 100 trillion tons of TNT. So it was a giant, massive explosion. And it was actually located underground, actually offshore in Mexico. And it's believed that the asteroid was about 10 kilometers wide and left a crater over 180 kilometers wide. And more recently in Chelyabinsk, Russia, in 2013, a large portion of the forest over a few hundred kilometers wide was impacted by a 20-meter long asteroid. And this asteroid let out more energy, about 6 to 33 times more than Hiroshima. Unfortunately, 3 lives were lost, but it was also in the middle of a Siberian forest. All right, let's move on to the next slide. And delving into a specific event, the Tunguska event happened in 1908. So this picture at the top is just a depiction of what happened. We don't have a photo, but it was an asteroid that made contact with Russia. And as you can see, the impact zone is larger than the area of Washington, D.C. And this picture down here at the bottom also just shows some of the larger impact zone. And on the right, you see that that's what this forested area looks like today. All right, we'll jump on to the next slide. We'll shift our focus over to planetary defense. So planetary defense involves the detecting, monitoring, and redirecting of NEOs. And all NEO is a near-Earth object. So asteroids are comets that fly pretty close by. So the difficulty in us for detecting, monitoring, and directing these is that these objects are very small in the scope of our solar system, and they're moving at incredibly fast speeds. So in order for us to track them, we've had to use different types of telescopes. So the first type of telescope is a ground-based, which is a lot easier to produce, but is prone to more errors, such as atmospheric distortion and interference. However, a space-based telescope would allow us to see more and different parts of the electromagnetic spectrum, but we would have to design a telescope that's more fit for space, and it's going to be a lot more expensive. An example of one of these telescopes is the NEO Surveyor or the Hubble telescope. And that moves on, or then we move on to the idea of removal. Can we somehow remove a NEO? So this is something that NASA DART mission aims to answer. And let's move on to the next slide. And this is just an image created by the International Astronomy Union. And it just shows some different initiatives and missions to help aid in planetary defense, such as the DART mission, which we're talking about today. All right, and we'll go on to our next topic.
So basically, the mission overview is basically what my previous partner said before, DART, which stands for Double Asteroid Redirection Test. Basically, it is a mission that NASA leads with multiple different scientific organizations and institutions that collaborate with NASA. The main objective of DART is to demonstrate the practicality as well as the effectiveness of the Earth's defense against hazardous and potentially hazardous near-Earth objects, mainly by redirecting a small asteroid through kinetic impact. The reason why DART is so important and holds significance is because it aims to provide insights into asteroid deflection and planetary defense strategies. DART includes things such as protecting the Earth from asteroids and even studying the compositions of asteroids. Didymos and Dimorphos are the two gigantic bodies that have gained a significant amount of attention due to both of them being involved with the DART mission. Didymos is the bigger body, while Dimorphos is the smaller moonlet. This binary system is significant because it was chosen for the DART mission, but also to learn more about asteroids in general. It was also chosen because of Dimorphos' orbit around the main asteroid, Didymos. This orbit was important to scientists because it allows them to gain valuable information about the characteristics and dynamics of binary asteroid systems. Finally, this binary system served as a testing ground for planetary defense strategies. And as we can see, this is basically what was launched to the asteroid to give it that kinetic impact and basically push it away from Earth.
So, given the fact that the spacecraft design instrumentation was set around the fact that it is supposed to be a kinetic solution for planetary defense, it is supposed to be a lower cost spacecraft. The spacecraft was actually totaled up to 30 million. And actually, for a space project, that's actually a relatively low cost. The main components in the spacecraft were rollout solar arrays, next ion thrusters, LiSSA-Cube, along with the Draco and SMART navigation system. And we're going to talk about that right now. So the rollout solar arrays, also known as ROSA, are extremely versatile solar panels that were revolutionary at the time of their implementation to the spacecraft. In fact, this is actually the first implementation of ROSA's kind, especially in aerospace. The design of the arrays and the fact that they can be rolled up like a carpet whenever necessary, and by the way, this was necessary during launch, along with their easily deployment. Their deployment did consist of some sort of spring mechanism, allows for overall more flexible utilization in a variety of space missions. These solar arrays can actually extend into 56 feet, and with that would actually allow optimal absorption of solar energy by increasing the overall surface area of the array. More surface area means that the solar's energy is actually able to make more contact area with the solar rays, which allows for more energy production. Given this, these solar panels are also relatively low cost, low mass, and ROSA, believe it or not, is actually a completely autonomous system, which means that it could deploy or roll up automatically without needing to be operated from the command center. Each solar panel is actually able to deliver nearly 30 kilowatts of energy, which is more than necessary for the components that are in the spacecraft. The efficiency of these solar panels are actually nearly up to 34%, which conventional solar arrays can only accomplish up to 20%. Given this, ROSA is a great thing that they implement to the spacecraft and can actually potentially further solar technology. Now, our next main component is the next ion thruster, NASA's Xenon thruster, which is kind of its longer name, is a very powerful ion thruster propulsion system that rivals its technology with conventional chemical propulsion systems. It is a completely electrical propulsion system that requires an output power range of 0.6 to 7.4 kilowatts, and is completely powered by ROSA. And ROSA is obviously very easily able to meet this output power range demand. The specific impulse is 4190 seconds. The higher the specific impulse, the more efficiency the thruster has, and the thruster efficiency of the system is actually nearly 70%. The thrust is measured to be 25 to 325 millinewtons, and can actually accelerate up to 90k miles. This versatility in power and thrust, along with previous utilization in space missions, meant that it was a perfect match for the DART system, because it can have a large range of power and can actually have a large and more versatile sort of movement. It can actually minimize the amount of flybys that the spacecraft needs to go through with its mission route in order to gain a boost. This can actually help in simplifying space missions. So we'll move on to our next component, which is the Lycia Cube. It was developed by the Italian Space Agency through a partnership between NASA and, again, the Italian Space Agency. Lycia Cube actually stands for Light Italian CubeSat for imaging of asteroids. The cube weighs approximately 14 kilograms and does have a propulsion capability of 56 meters per second. It actually does use two optical cameras, which are named Leia and Luke, for imaging Star Wars fans. And its purpose was to actually capture the imaging of the impact, the ejecta plume, and the resultant crater of the impact of the spacecraft that it would have against its target asteroid. After it takes its photos, Lycia Cube will then transmit these images back to Earth. Now, the big question is, how does the spacecraft actually navigate to the asteroid, which brings us to our next main component. The Draco and Smart Navigation System, also known as Didymos, Reconnaissance, and Asteroid Camera for OpNav, and the Small Body Maneuvering Autonomous Real-Time Navigation System, had a very, very big role in navigation of the DART spacecraft, of its navigation. Draco's purpose was to provide approach images to the Smart Nav algorithm to allow for precise targeting of the asteroid, while providing high-resolution imaging of the surface of the asteroid to match characterizations of the target body. Draco's design uses multiple subsystems to achieve this photo imaging. Draco does use an optical telescope assembly, which uses a Ritchie-Chrétien design with hyperbolic primary and secondary mirror and field filing lens. When Draco would then translate these images to the Smart Navigation System, which, by the way, the Smart Navigation System was completely autonomous and, again, did not require any sort of correction maneuvers implemented by a command center. In a way, it was almost implemented nearly identical to how you design a self-guided missile. Together, the Draco and Smart Navigation System would correctly guide the spacecraft into a target asteroid by the following sequence. Draco would locate the target asteroid by matching the image captured through its lenses with a blobbing algorithm. And you can actually see the image, that in the image on the right. The blobbing algorithm would then help identify the blobs of light that correspond to the target asteroid. Once identified, the system would find the center of the asteroid for the target to make contact with, again, it's a kinetic spacecraft. Then through a series of calculations and preset algorithms, the guidance filter would then decide to head towards the asteroid and automatically perform corrective maneuvers to guarantee that the spacecraft would remain on course for its target collision.
All right, so one of the implications for the future is the post-impact simulations of the DART-like impact to study the effect of angled impact on momentum enhancement and ejecta properties for low-strength material. The simulations show the ratio of the net ejecta momentum, which increases with decreasing cohesive strength, leading to larger crater volumes and more ejected mass. Also, the ejecta angle decreases with the lower cohesion due to the delayed crater growth, resulting in more vertical ejection of the material. The simulations reveal differences in N and alpha for the impacts to cohesionless oblate and brolate spheroids with the same mechanical properties, partially influenced by the size of the impacted target. Next slide, please. Also, understanding the beta, which is the momentum enhancement factor, is a key component in predicting the outcome of the dart impact on dimorphos because it studies the efficiency of the deflection following a kinetic impact. Beta values influenced by factors like friction and cohesion, which dominate over porosity. Simulations demonstrate that different combinations of the material properties can yield similar beta values, but these impacts can produce different crater morphologies. For example, impacts into stronger, non-porous surfaces can result in the same beta as impact into weaker porous surfaces, but the resulting crater differ significantly in size. Add to that, when DART is modeled as spherical impactor with mass equivalent to expected spacecraft at impact, the simulation tend to exaggerate both the momentum enhancement and the size of the resulting crater compared to simulations that account for the spacecraft's complex structure. In these simplified simulations, there is an average of overestimation of approximately 5% to 20% in the momentum enhancement factor, beta, as well as the crater size is significantly overestimated, with increasing range from 79% to 147% in comparison to simulations that consider this spacecraft design. Next slide. The future projects after DART is the HERA mission, which is a European Space Agency, which was designed by the European Space Agency, which is going to launch in October 2024. It promises to provide a deeper understanding of post-impact simulation, which will arrive in 2026. Next slide. HERA's goal is to comprehensively characterize dimorphos, the moonlet orbiting by accurately measuring the mass and assessing the size of the impacted crater resulting from the DART mission. HERA will significantly contribute to our knowledge of the NEO threat. In addition to that, it will also investigate the potential deformation. Next slide. The data HERA collects will be valuable to refine our understanding of the quantity, composition of ejecta produced by the impact, offering profound insight into dynamic of NEO deflection and the strategies we can employ to ensure the safety of our planet in the future. And this picture is the spacecraft of the HERA mission. So that was our presentation for today. We talked about NASA's double asteroid redirection test DART mission, which was successful to use the kinetic impactor to alter an asteroid, which is a great achievement in planetary defense. Thank you for listening.
Thank you.